Okay. Good morning, girls.
You are now unmuted.
Okay, good morning, girls. Looks like we have 8 people here. Okay, that is not bad. Okay, so yeah, I'll just quickly review what was done in the last class, and also we can proceed with the next topics. Is my voice clear, girls? Can you all hear me? Hello? Okay, so today's topic is so last time we were discussing about shunt compensation and how shunt compensation is available, so is useful for transient stability and voltage regulation and improve the transmission efficiency of the transmission line. And now today we are going to see methods of controllable var generation and in particular we are going to see today one of the SVC static var compensator. Okay, so different methods of var compensation. Methods of var compensation generation is like this. So the capacitors generate and reactors absorb. This is reactive power when it is connected to AC power source. This is the main intuition you should remember. Like what does the capacitor do? Capacitors are inductors. Capacitors do generate reactive power, whereas inductors absorb any extra reactive power. And we know, right, in case of load carrying conditions we can see two different conditions. One is under voltage, another is over voltage. In case of under voltage, the voltage level is less than what is required. In those cases, capacitors help us capacitors help us to Capacitors help us to generate more reactive power, so to compensate that fall in voltage instability. Similarly, in cases when we have under voltage, like when we have over voltage, when the conditions of load is very less, means like the uh, that is like light load conditions. When we have very less load, then we go for reactors. What do they do? They say that already the reactive power is so much high, that is why voltage levels are high, but we need to bring back them to flat voltages. That is why we need reactors. So both of them are needed. They have been used with mechanical switches for controlled var generation and observed since the early days in AC transmission line. It is a low cost option. So in olden days they used to use mechanical switches because of their affordability. They are low cost options. Right now, because of PE, that is power electronics, we are opting for power electronics. So what are the other ones? Other ways of controlling volt via var generation. One is mechanical switches, and another is continuously variable var generation and absorption by dynamic system compensation was originally provided by over and under excited rotating synchronous machines. So, synchronous missions you already studied in previous course, right? Like, what do synchronous missions do? When you over excite or under excite, according to that, it will generate reactive power. If it is generate or absorb reactive power, it can do two things. And these synchronous missions are still in use. People are still using them, and these mechanical switches are also there. It's not like only new things are coming up. The old things are still there, and synchronized generators are still a popular choice. Why? Because of their affordability, and also the technology is very old, so people know how to operate this. So when you under excite, what happens? It acts like a inductor. When you under excite, it acts like an inductor. When you over excite, it acts like a capacitor. Okay, these are the two things that a synchronous machine does by saturating reactors in conjunction with fixed capacitor. So it can be later, it can be added with saturation reactors or capacitors. Actually, it does work the same way. Since the early 1970s, high power line commutated thyristors in conjunction is nothing but in addition to. So with capacitors and reactor have been employed in various circuit configurations to provide what? Variable reactive power. So since 1970s we have seen a very vast development in thyristors. Okay, so the Thyristor technology is so improved now that we are employing the Thyristor controlled and Thyristor switched capacitor and reactor for our variable var generations. In olden days, there was mechanical switches. Then we have synchronous machines. Now we have Thyristor controlled var generation. Okay, this in effect provide a variable shunt impedance by synchronously switching shunt capacitors or reactors in and out of the network. So how is it possible? By varying the shunt impedance, by switching on and off. By switching and on and off, we are varying the shunt impedance. Using appropriate switch control, the var output can be controlled continuously from maximum capacitive to maximum inductive output at a given bus voltage. Using appropriate switch control, meaning uh, the way how we turn on and turn off these devices, the var output can be controlled to maximum in the capacitive means maximum high generation reactive power generation to the maximum inductive, meaning like the most you can observe, most reactive power you can observe from a bus voltage, so bus from a system to be exact. All of the different semiconductor power circuits with their internal control enable them to provide var output proportion to the input reference. So what do they do is, if you want to control something, you should have a reference like how much is extra that is going there. Let's say for example, the voltage, the output volt the line voltage has raised up. Let us say it should be at 1 point per unit, 1 per unit, but what happened, because of light load condition, because of a very less load condition, the voltage level shoot up to 1.05, which is not correct, like which is not the within the range of operation, or maybe it's very near to the maximum range of operation, so we have to bring it down to 1 per unit. So you see, we are taking the output 1.0 and we are taking some reference point, then we are comparing. So this is taken care, this comparison, like the difference is point 0.5, point 0.05. So point 0.05 uh, is the value that should be taken care using reactive power. So this all thing is taken care by internal control circuit using input reference and what is the output proportional. And the term are collectively, so all the different semiconductor circuits with internal control enable them to produce var output uh, proportional to input reference, are collectively termed by joint EEE and CGRI definition as static var generators. So all these semiconductor circuits which has this input and output control using internal control These devices are called as static var generators. The static var compensator is a IEEE CGRI core definition, a static var generation whose output is varied so as to maintain or control specific parameters such as voltage, frequency of the electric subsystem. So this is a term. These two are similar. This is compensator, this is generator. Static var generator is self-sufficiently functioning device that draws controllable reactive current from alternating power source. So the control input of var generator can be arbitrary within the operating range. Reactive current, impedance, or power reference signal that SVG is to establish. So obviously, I told you now. So based on some reference signal, like based on some what is the output that is given there and how much you have to control. This is taken care by self-sufficiently by the internal control. Thus, static generation can be verified as a viewed as a power amplifier that faithfully reproduces the reference signal of the desired voltage. Okay. Okay. So they say that according to IEEE CGRI definition, a static var generator becomes a static var compensator when it is equipped with special or external or special system control which derive the. So they say when you actually they are used very um, for they can be used in the same way, but the only difference that makes a static generator different from a compensator is it has a extra circuit for control in addition to whatever internal they have. If you add an extra control, then it becomes a static generator. So let us not worry about so much of static generator. Just worry what is a static var compensator. Static var compensator does two things. It can either generate reactive power or absorb reactive power using what? Inductive for observing and capacitive for generating reactive power. Okay, and this is how this is done using internal control circuit. Modern static generators is based on high power semiconductor switching circuits. These are inherently determine some of the operating characteristics such as so we are going to see operating characteristics of these static var compensators. And girls, remember uh, the the VI characteristics are very important. You have to learn those VI characteristics, which we'll see in next few slides. So, what are the different operating characteristics they look for? Usually, they look for applied voltage versus obtainable reactive power current, VI characteristics, harmonic generation, losses versus VI output. These are different operating characteristics a static generator provides us. So, we have to make use of them. And available response time, setting limits for the achievable performance and independent of external control. Ultimately, also the that of so these are certain operating characteristics we look into when we are talking about any static var generator or a compensator. The main thing that we here in this unit are discussing about VI characteristics, nothing but applied voltage versus applied obtainable reactive output current. This is the one. Okay, if you understand the characteristics of that, then you will know where to use which compensator. The two main sections describe the operating principles and characteristics of two types of static var generator presently used. Those are which employ static thyristor controlled reactors with fixed and thyristor switched capacitors to realize variable impedance, and they also imply switching power converters to control synchronous generator voltage. So first thing is we had to think about two things. First of all, we thought we have different kinds of var generator. One is a fixed capacitor and reactor one, and the other one is a synchronous generator one, and the third one is a thyristor one. In under thyristor one, we basically do both absorption and generation of reactive power. And how do they do? They use capacitive power and inductive power to compensate our reactive power. Okay, and then a static generator give us different operating characteristics based on which we design our compensator. The basic thing why what we have to do here is designing a compensator. So for that we need to know the VI characteristics. What are the VI characteristics? Applied voltage versus obtainable reactive power input. So under static var generators we have two things. One is thyristor controlled reactor or capacitor, or thyristor switched capacitor or reactive or reactors. Okay. So here, like in a whole view, I have shown you like in a one place what are different things that we can do. So why do we go for shunt compensation? Especially, we go for shunt compensation for voltage control and load stabilization. Where do we install them? Usually, we install them at the midpoint of the lines or at the edges of the transmission lines. And what is the other added benefit of it? It takes care of power factor, and also it takes care of what damping oscillations. Okay, so these are the beauty benefits of having shunt compensation. And then different kinds of shunt compensators. We have static var compensators and the static synchronous compensator and static condenser. Static condenser is nothing but your static mission that I already discussed about. Okay, static var compensators. Today we are going to see static var compensators. So again, these static var generators are divided based on uh, control technique. Especially here we are changing variable impedance type static var generator. Under that we have, if we are changing the impedance, then these are different types of static var generator. First one is thyristor controlled or switched reactor, TCR or TSR. And then thyristor switched capacitor, TSC. Fixed capacitor thyristor controlled reactor, TC. So we'll have both of them there, a fixed capacitor and TCR. And then we have thyristor switched capacitor and thyristor controlled reactor. Okay, TCR or TSC. Switching converter type var generators, static condenser and static compensator. Okay, so when we are using switching type converter, then we go for, there is one more thing like statcom. So this is again very important. So they basically say this all as SVC. Static var compensator. We know the differences between also. We have mainly two things. One is static var compensator and one is statcom, and another one is our synchronous condenser or machine. So today we are going to see static var compensator. At least we'll try to cover some of the types. So this is a substation. You guys can see this is like a blueprint of a substation where you have different types of things going on here. Static var compensator transformer here, harmonic filters. We have here a control room when we have thyristor valves like VSC, I guess. And then thyristor controlled reactors. Here we have a reactors, and we have thyristor switched capacitors, TSC, TSC, TCR. So this is how a typical substation looks. at the high voltage level. And also remember girls, this they do at very high voltage levels. Okay, so static var compensator under comes under what? Variable impedance, where the current through a reactor is controlled using back to back thyristor valves. We see that picture. It's okay, one more thing girls, static var compensator na can be. So you see, TCSR, you can be just one item like TCSR. It can be just one item like a TCSC. So that it can be mechanically switched capacitor, mechanically switched inductor, and also SVC can be combination of all this also. Okay, you guys get it? So it can be just TCR, or it can be just TSC. TCR means Thyristor Controlled Reactor. TCSC means Thyristor Switched Capacitor. And it can be fixed capacitors, nothing but mechanically switched capacitors, or fixed reactors. And also, when you say the term SVC, it can be just one thing, or it can be combination of all these things. Okay, you understand? When they say SVC, it can be just one this thing, or one this thing, or it can be combination of all. Why? Because we mostly they there may be situations where you need to add reactive, nothing but we need inductive power compensation, like inductive loads, and also we need a capacitive compensation. So in that way we can use both of them. That is the reason you see this is and more. This is a typical static var, and this is called system. Why? Because different items are there, that is why it is called system. People use SVS or SVC combinedly. So SVC means static var system. A system is a combination of different devices. And SVC, this whole thing can be called as one compensator. So this is how typically you see in a very large high voltage transmission system. Okay, so here we have high voltage bus, we have a potential transformer, we have a this is for current. So current transformer we have, and then we have a filter for harmonics, we have a TCR, we have a TSC, and we have a controllers. You see, we have everything. We can have all of them, or just one of them. Okay, so that is the TC, that is a static var compensator. The application of static var compensator was initially for load compensation, for especially. Okay, girls, we discussed, right? Where do we use them? When they are specially used for load compensation of fast changing loads such as steel mills and arc furnaces. Remember, we have studied arc furnaces and UW, where we need high arc in a very short period of time. Such kind of times, what happens? We need very sharp, high voltage and high ramp up and high ramp down. So in those cases, the load compensation can be easily done with SVC. Okay. Here the objective is to provide dynamic power factor improvement and also balance the currents on the source side whenever it is required. The term static is used to denote not rotating. You see, we have been using static, right? What is static means? It's not moving. It's not rotating. There is no rotating part in it. Actually, that is the beauty of it. Compared to our synchronous compensators, they have rotating parts, So they have losses. Whenever there is any rotating part, you obviously see more losses. But this is our thyristor. Thyristors are there, so thyristor walls are not rotating, and so they give less losses compared to synchronous compensators. And here are the objectives of our SVC: increased power transformer, because we are reducing losses by maintaining the voltage, and also we are maintaining power factor also. That is the reason we can improve the uh, power transfer capacity, and then improve stability first for fast voltage regulation. Whenever we need fast voltage regulation and dynamic power factor, then we go for SVC. Then damp low frequency oscillation due to swing modes, and damp subsynchronous frequency oscillation. So these are different oscillations we can control using the same SVC. And dynamics over voltage control. A SVC has no inertia compared to synchronous condensers and can be extremely fast in response to 2 to 3 cycles. And one more thing, girls, whenever we are discussing about compensation, now we discuss, like, we have to know like how fast they can provide compensation is also very important. Okay, some synchronous condensers, they have some inertia, right? So they'll take some time to start on. So they are called. So I could not recall exact the terminology we use, but mm, uh, it's like there are some compensator that come online or hotline by 30 minutes. There are some compensator that come very quickly. So SVC is one such thing that comes very quickly and takes care of fast control reactive power compensation. Okay. Shunt connected static var generators are observers whose output are varied so as to control specific quantity parameters. The basic types of SVCs are, we already discussed, right? What are the basic types of SVCs? Thyristor controlled or switched reactors, and then TCSC, and then a fixed. I think I reiterated it here, but you guys can see this can be combination of all of them or some of them. That is the main thing you have to understand. What is a compensator? You call this as a SVC and you call that as an SVC, but however, both are SVC. Only thing is, it can be combination of also. So that is the fact. And then the SVS is aggregation of SVCs and mechanically switched capacitors whose outputs are coordinated. And again, SVS means static var system. Whenever somebody is calling something as a system, meaning it has some other devices or some yeah, especially devices, when we group together and we call it as a system. When operating is in its capacitor limit, an SVC behaves like a simple capacitor. I think you guys know the opposite of it, right? When it is operating like a inductive, then it absorbs reactive power. Then it acts like a simple inductor or reactor. So the first item is static var compensator. What is that? TCR, Thyristor Controlled Reactor. So by now you already know this is the figure of thyristor TCR. So you see back to back connected our thyristors. Drop across it is VT, and we have an inductor in series with this back to back connected thyristor wall. This is the figure. This is the very simplest figure of our TCR. TCR mainly used mainly to observe excess of reactive power in the system. Single phase thyristor controlled reactor is consists of fixed, usually air core reactor in of inductance L. This, and we have bidirectional thyristor valve, back to back connected thyristor valve here. And you see, girls, this is the difference between power electronics and electronics. What kind of voltage these thyristors are taking? The thyristors can take up to 4 kV to 10 kV. And what kind of current it can have? 6 kA to 3 kA, 3 kA to 6 kA, kiloamperes. This is a very high current. And the voltage 4 kilovolt to 10 kilowatt. This is very high voltages and very high currents. So that is why we use thyristors, not transistors. Thyristors in our power electronics, in our power system, where the voltage and current ratings are very high. Thyristor valve can be brought down through a conduction by simultaneous application of gate pulses. So we are giving gate pulses for all for the same polarity. So we, how do we turn on and turn off these thyristors? By using required gate pulses. So we'll see little bit detail into how it is done. TCR is a variable impedance type, is SVC, and current in reactor is controlled from maximum to zero by firing angle delay. By what? By firing angle delay. That is how we are controlling the flow. Maximum to zero you can make. SCR is delay with respect to peak of applied voltage in each half cycle. So how it is delayed? It should have some reference, right? So what is the reference now? Whenever this is at after our applied voltage reaches a, when alpha is equal to 0, SCR closes at a peak of the applied voltage, results in current in reactor which is the same as that of obtained when switch is completely closed. I'll just okay, looks like this is wait, okay. So you see, this is our applied voltage, girls. Okay. So here, when applied voltage highest peak, they call this different names: peak, crest voltage, peak voltage. Anything is same. Maximum voltage when it is maximum. Okay, when our voltage is maximum, then what happens? Now the current through thyristor firing angle. This is alpha is our firing angle. See, alpha is our firing angle. So what happens? And this dou is our conduction angle. You might have known already from your power electronics what is a firing angle, what is a conduction angle, right? Conduction angle is nothing but when our thyristor is on, when it is conducting. Firing angle is nothing but the angle at which the thyristor gate pulses are given to thyristor to turn on, right? So this is the current through our inductor and the back to back thyristors when alpha is 0, meaning when 0 firing angle is given, this is how your current looks like. Okay, when okay, so what happens? This is how it looks like. But what happens? Uh, if we give a firing angle of alpha, okay, let's say it can be anything like 20 degrees, 30 degrees, 60 degrees. Let us assume we took some maybe 30 degrees. So now our current will be low, and also the time is also low. This is how it happens. and this value, this voltage is given by V by this uh, this what is it, impedance. How much impedance we change is given by V by omega L sine alpha. Alpha is nothing but firing angle. The more firing angle you will change, it will become firing angle. Zero means what? Zero. Zero current is conducting. And when firing angle is 90 means what? When we have firing angle 90 means that is a maximum. So that is a maximum impedance that you get. Okay. So again, this is one more example, girls. So this is positive half cycle. Here they are showing negative half cycle. What happens during negative half cycle? It is the same. This thing is called offset, girls. This much offset you got because of this firing angle. When it is positive, this is called minus. Negative offset, this is in negative half cycle, it is positive offset. You see, is a constant, is positive offset and negative offset for respective to half cycles. Okay, so under negative half cycle, this is the positive offset. So same thing, girls. When it is in the middle, when and, even under negative obstacle, when it's maximum, this is zero. When alpha is zero, when I is when we have some certain firing angle, and this much is the conduction angle. Okay. Any question, girls? Till there, it's quite far straightforward. And then static Var compensator, TCS are the same. The delta, the delay angle, the delay angle alpha, then the conduction angle is alpha is equal to 2 pi minus alpha, this thing, alpha. Thus, the delay angle alpha increases, the corresponding offset increases, uh, resulting in the reduction of conduction angle. So if you don't turn off for so long time, your conduction, your turn on period will be also very less, right? If you if you turn if your firing angle is very low, then your conduction period it will be high, right? So same thing. That is what it says. So what does it do? It basically changes the reactive current at the maximum delay, that is sine all the sine 90, right? And we had maximum angle 90. So maximum delay alpha is equal to 90. The offset also reaches maximum, that is v v omega l dash, at which both conduction and reactive becomes zero, right? Obviously. So here they give you some examples when alpha is equal to zero. However, thyristor TCR current is. So this is the current, gas. This is the TCR current that we are talking about. This is the voltage. Okay, when alpha is 30 degrees. So you see, we did not turn on till this point. So our TCR reduced. And same thing. This is a MATLAB program, I think. You can also write the same MATLAB program. Just use these equations. And now, when the gating of the valve is delayed by angle alpha, between where alpha lies between 0 to pi by 2, with respect to crest or peak of the voltage, the current in the reactor can be expressed as like this. This is the equation. When V is equal to cos omega t and alpha lies between 0 to pi by 2, we can give the current flowing. The current flowing through this is given by the equation I IL of t is equal to 1 by L integration from alpha, that is nothing but where you are firing angle, to omega t, that your cycle. So it will give V by omega L sine omega t minus sine alpha. The amplitude, amplitude I alpha, ILF at alpha of the fundamental reactive component of the current can be expressed. So when you are using the Taylor series and trying to find the fundamental component, this is your value. ILF alpha is given by V by omega L 1 minus 2 pi by 2 pi alpha minus 1 by pi sine 2 alpha. Okay, what if this is when we fixed the alpha is equal to 30, when we fixed alpha is equal to 0, what if we are continuously changing the alpha value? What happens? By continuously changing alpha, the firing angle, you'll gradually change the firing angle. What is it does? It is usually used for damping oscillations, meaning if there are any damping oscillation at that point of time, instead of fixed alpha, they continuously vary the alpha. You can dynamically control the power required by the reactive power in each half cycle. So in each half cycle, we make it bigger. So you see, this is our V. This is our V, right? Okay, this is nothing but this V, girls. Okay, now what happened? This is our current, like this IL, this current. So this is first cycle. In the first cycle, 0 alpha. So here it starts. So alpha is 0, means no firing angle is given. So it directly turns on as you turn on this. As it reaches the peak, it directly turns on. So first half cycle is done. So when it is going for negative half cycle, what we did here, again it came to here, right? Peak of the in the negative half cycle, peak of the voltage has come. So now what we are doing, we are giving some alpha firing angle, some firing angle we gave. So now let me change this color to yellow, black maybe. Black is already there, right? So this is how it was going before. Okay, because of this small gap, it started. Now this value also reduced if you pay attention to. Okay, and now the half cycle has come again. Here some gap because of the previous firing angle. Okay. Okay, this is something we have to, you'll get in the next sessions. um, this is like a, you can just directly turn on and turn off like that. There is something like turn off angle also, so that is the angle here. Okay, and then we have here some firing angle, and then again same thing goes. So now our alpha is equal to alpha 2, so it became much less. Okay, this is a, again what is this called, the critical angle. So like it's not critical angle, it's like before you turn off also you should have follow some angle. Okay, so again we got here like 90 degrees, so we don't proceed, we wait for the firing angle. The firing angle is much increased now. Now we are moving towards this much. This is a turn off angle, and then we wait for our firing angle. So the firing angle is much increased now when alpha is equal to alpha 4, when alpha is equal to alpha 3. This is the thing. Okay, then We proceed, and this is much less. So basically the voltage across is that thing also is reducing. If you see, very less. So this voltage across VLF, sorry, it was previously following the same, but however this one also in decreasing. So you see the oscillations are damped so much. That is the idea, girls. We are damping the oscillations using continuous firing angle. Is it clear? And similarly, we have an equation for BL, that is nothing but admittance. So this is the equation for admittance. When alpha is the firing angle, when we have alpha angle, then we have 1 by omega L, 1 minus 2 by pi alpha minus 1 by pi sine 2 alpha. It looks very similar to this one. You see, only difference is 1 by omega L. Why? Because remember this is admittance, right? Current. If you see V is equal to IR, so I is equal to V by R. So 1 by R is nothing but admittance. So this is it. So what happens when we draw when we draw when we try to draw a figure with this? So we have ILF in per unit using this one, and what is the delta? How are you going to vary using different delta? So this is the ILF. This is two of our this thing. So this is ILF. So when we have this one is 1 minus 2 pi, when we have 1 minus 1 minus if you what happens if if you have only these two terms, what if happens if you have only all of this term, what happens if you have only these two, what happens if you have only one these two. So this is how they are drawn a picture: amplitude variation of fundamental TCR current with the delay. How much amplitude is varied if you keep on varying your alpha? Okay, and this is very important, girls. So you have to know like VI characteristics of TCR. Remember, this is a reactor. You'll see capacitor also, but this is a reactor. So we are drawing voltage across the thyristors. This is VT. See VT, and then current through that. So you see, we got BL max, maximum inductance of TCR, and so by varying the TC admittance, this shaded part is called operating region, girls. This shaded part is called operating region. What is the operating region? Meaning like you see till this currents. So for various values of voltages, the current is varied in this fashion. So for this voltage, this much current you can expect. For this voltage, this much current you can expect. So this much current, that the maximum current, right? Okay, the operating voltage. So for this much voltage, this much current flow you can expect. Same goes. So maximum V, maximum I. Okay, and remember, because this is a capacitor reactor, we got this side. We will see TCS, TSC. In that, we'll get this side. This is inductive. That is capacitive. So another item is how harmonics. are changed. That in a TCR, in addition to wanted fundamental currents, also generate. Okay, the problem with this now, it also generates the harmonics. For example, they say that that is the main problem when we have power electronics in our power system. It will do the good job, but also it will pollute our power system. How? By giving some harmonics. So you see different harmonics: 11th harmonic, ninth harmonic, 7th harmonic, 5th harmonic. This is how the fundamental harmonic looks like. By changing the delay angle, how many harmonics are there? Okay, this we'll see tomorrow, girls. Okay, I think, yeah, I have no time now. Like I hardly have 5 minutes. Okay, this is only one slide. Now I'll finish it quickly. So last we have discussed TCR, Thyristor Controlled Reactor. We have another thing as TSR. It is switched. So it is a special case of TCR. What does it do? It does not do variable, like it will not have this much variation. You saw, right? We have variations now. But in this one, it can be either only fully turned on or fully turned off. Only two things can happen in a TCR. If a thyristor valve is fired exactly at the voltage peaks accordingly at alpha 90, the forward thyristor valve TS1 and alpha is equal to 270, the reverse thyristor T2, the maximum inductant current flows. So what happens? If you turn on, it will completely go into this position. Otherwise, it will go in this position. There is no middle thing. Okay, only two operating conditions it has. Okay. Um, if no firing pulses are issued, the TCR will remain in a blocked off state. No current flow. So if you don't turn on or turn off, it will not do anything. The TCR ensures rapid availability of a rated inductive reactive power system. Remember, girls, I said now whenever we want, like sometimes we need this much high position in one instant. In those cases, we go for TCR. Sorry, TSR. Okay, the difference between TCR and TSR is TCR is we can have variable firing angle option, whereas in TSR we have either turn on or turn off. Only two options available. Okay, so that ends the class today, and tomorrow we will see TSC. Okay, and operating characteristics of TSC also. You see, this is this side. Okay, and if then we'll see combination of these two. With that, we can complete today's session.